And hello, welcome to this video of natural convection. So last time I was talking about low Prandtl number fluids. Okay, I just left it off as this important number is the Boussinesq number, and it is different from the important number for when Prandtl numbers are like comparable to 1, if not greater than 1. Okay, so this is a pretty much more exotic case, as I was saying. So yeah, let's look at some solution procedures before we call it before we conclude. In our boundary layer solutions, there will be the integral solution. Okay, the integral solution, and then there will be the similarity solution. Of course, we can just use a hardcore CFD on the thing. Okay, so let's go with integral solution first. It's like the most intuitive. Okay, so I will just uncomment all of this and let's do a quick compile. Alright, so to solve our equation, we need to know what we are going for. Okay, otherwise we'll be going in circles because there's lots of things. Okay, so let's just be very clear what we want to answer, what questions we want to answer. So what are the questions we want to answer? Okay, first is what is the Nusselt number? Okay, we are most interested in the heat transfer coefficient, or at least so we want to find out some expression for the Nusselt number. We want to also know roughly what the velocity profile is like. Okay, we want to know what the velocity profile is like. And last but not least, we want to roughly know the ratios of this boundary layer thickness, okay, between the thermal and momentum boundary layer. Okay, so so we may not actually just solve everything here. We may solve it for like special cases, for example, high Prandtl number and low Prandtl number fluids. Now, since low Prandtl number fluids are more of an exotic case, I will not touch them as much. I will focus more on high Prandtl number because that's more common. Okay, because liquid metal heat transfer is not as common. Okay, unless you work with very specialized cases. Yeah. So anyway, I want to focus more on high Prandtl number fluids. Okay, so we'll look at the case where we have high Prandtl number. I just brought down the momentum equation from here. Remember, we have our special Rayleigh number. We have our special ratio here, delta T to H. Okay, and delta T to H, and we have our other terms as well. Now, if our Prandtl number is exceedingly high, these terms can just be dropped off. And we have a rather simple equation here, where the temperature profile directly dictates the velocity profile, at least inside the thermal boundary layer. Okay, which again I emphasize it's smaller than the momentum boundary layer. Now, from this equation here, what can we sort of find out? Okay, we can find out something quite interesting. We can find out how the boundary layer actually grows. Okay, how the boundary layer actually grows with, let's say, your height. Okay. So how does the boundary layer grow with height? So how we take a look at this equation here is this. Notice this term here is on the order of magnitude of 1. Okay, this term here is on the order of magnitude of 1. Whereas theta is also on the order of magnitude of 1. That's how we non-dimensionalize our terms. So from this we can see that this term here, delta T over H to the power of 4 times the Rayleigh number, is also on the order of magnitude of 1. So if you just do some simple rearrangement, okay, delta T over H4, delta T4 over H4, okay, I'll just bring the H4 to the other side, and then I will just take the whole power to the 1 over 4th power. So that I will have delta T equals to, will be on the order of magnitude of H times the Rayleigh number to the power of minus 1 over 4. Okay, remember the Rayleigh number is actually dependent on the H as well. In fact, there's a H cubed power over here Alright, there's a h cubed power over here. So if you take it to the power 1 over 4, it will just be 3/4. Okay, 3/4. So there will be h to the power of minus 3 over 4 here, and then h to the power of 1. Okay, so let's just make it clearer here. Okay, and instead of using k here, I will just use the something like math cal order of magnitude of 1. Alright, just to make sure that you can see its dependence on h, I will substitute back the Rayleigh number here. Okay, this is an interesting insight. Now substitute the Rayleigh number back in here. There's the Rayleigh number here, and we shall see what actually comes about. Okay, we can see the dependence on h is you can see it here. Okay, so h to the power of minus 1 over 4 becomes h to the power of 3 over 4. So I can just take this out of here, and I'll put h to the power of 1 over 4 on the outside. So you can see this this h is actually dependent on 1/4 the height. Okay, 1/4 not 1/4 the height to the power of 1 over 4. Okay, so so more or less if we plot that graph out. Okay, if we have our wall again, if we have our wall again, then we have our growing boundary layer. Okay, so we can say for high parental number fluids, okay, the thermal boundary layer thickness will go as h to the power of 1 over 4. So this is the rough correct shape, unless my drawing is really bad and all. Yeah, but this kind of shape should be expected for the laminar part of the boundary layer. Okay, for high parental number fluids. So nothing too bad there. This gives us a good insight. And based on this, we can start to guess what our velocity profile might look like. Okay, how does it scale? How does this velocity, how does the maximum velocity, so to speak, scale? Okay. So remember, this is the order of magnitude of our velocity. Okay, or we can say that we can also say that the velocity will be on the order of magnitude of 1. Okay, times this value here. Okay, and of course, now we can just substitute this whole thing in here, okay, which I will not do as much. I can just do a dot here. Okay, delta t will scale as h to the power of 1 over 4. Okay, so delta t will increase with h, but this thing should scale. Okay, should scale. I wonder how to do the squiggly line thing in LaTeX. Hold on. Okay, so the thing. Okay, in math mode, I think LaTeX says this Stack Overflow, Stack Exchange says sim. So v will be sim, will be tilde, that tilde symbol thingy. It will go as, if I'm not wrong, h to the power of 0.5. Of course, there are lots of other terms which I didn't bother writing it there. Okay, but okay, this is a very nice tilde. Yeah, so the velocity will scale as h to the 0.5 power. Okay, we're not talking about velocity profile just yet. Okay, this is just how the velocity scales with us going up. Okay. Excuse me. Yeah, this is how the velocity will scale as we go up the height. So what about, so this will give us roughly what the velocity well, part of the answer of a velocity profile. It will scale as a h to the half based on our scaling analysis. The boundary layer thickness will grow as h to the power 1 over 4. Okay, and what about a Nusselt number? Okay, Nusselt number, then okay, we'll have to do a little bit more work. We have to go back to our equations. Okay, so let's go. Yeah. So how do we actually solve this thing? Okay. So yeah, I've not actually gone into integral solution just yet, but integral solution basically the idea is this. Okay. So what we do is that we have our boundary layer equations already derived. Okay, a boundary layer equation. So the E is really out of shape. Boundary layer equations. Okay, what do? Okay, we integrate them across the whole boundary layer. Okay, we integrate them across from 0 to, let's say, x equals to delta. Okay, delta t or delta p. Okay, where this is the momentum boundary layer thickness. Okay, dx. So we are integrating it across the whole boundary layer. The other way of looking at this is with the control volume analysis, which I will not be doing because I already did that the last few times, and I kind of shown that well, roughly with this integral solution, you can just, as the name suggests, just integrate across the whole boundary layer. This is an approximate solution. Okay, what do you do once you integrate all your equations? Okay, you substitute assumed velocity profile. Okay, velocity profile. Substitute assumed velocity profile and cross your fingers, hope for the best kind of thing. So with your laminar hydrodynamic boundary layer in a forced convection, what you do is you assume a cubic velocity profile. Okay, with the other one, yeah, with this, yeah, this is more or less how you do it. The other part is pretty straightforward. However, in this boundary layer, in this boundary layer, you can't actually just assume a cubic velocity profile. Why? Because if you take a look, I mean, based on what we were talking about, we said we have at least our thermal profile should at least be a downward slope. I don't know what kind of slope this is. So this is a temperature versus like x, right? Okay, and at the same time, you will have a no slip condition at the wall. Then the velocity will reach some maximum, I don't know where, and then it start to drop off. Okay, this is u versus x. Now, does this look cubic to you? Okay, this doesn't actually look really cubic. It looks more like some exponential multiplication kind of thing. So there's some asymptote here, and it goes up and goes down. Okay, so what's a good function to describe this shape? Okay, we are not that sure yet, but maybe we can start with the easier problem, because eventually we will need to substitute a temperature profile in there anyway. We can actually look at this temperature profile here. Okay, so we are trying to guess a temperature profile. Okay, so yeah, so heat transfer. Here, heat transfer in the x direction is how is it being determined? Okay, so well, we in our energy balance equation, okay, heat transfer is the equations are as follows here. You have your Laplacian term to the right, which describes conduction along the x direction. And then you have your advection terms here. One for a x direction advection, one for the v direction advection. Okay, so to have a rough guess of the what do you call that? Yeah, to have a rough guess of the boundary the temperature profile. Sorry, so we are having a rough guess of this temperature profile so that we can have a rough guess of we can have a rough guess of temperature profile and velocity profile so that later on, after we integrate, we can substitute back in some at least decent guesses of these temperature and velocity profile. Okay, I'm not going to spend, I try not to spend too much time, but I will try to spend enough time so that none of this should be too confusing. Okay, so if we were to do some scaling analysis again, okay, along the y direction, okay, okay, we can see that dt dx, the temperature gradient here, it actually scales as Ts minus T infinity, which is quite obvious, and of course the delta T, which is the thermal boundary layer kind of thing. Okay, and of course U is the velocity. So if we just want to get rid of all the velocity dependent terms, we know that U actually scales as alpha over delta T. So let's see. Okay, where's my stuff? Yeah, okay. U scales as alpha over delta T. Okay, U scales as alpha over delta T, so dt dx. Okay, so this is the how the thing scales along the y direction. Okay, I'll just copy and paste it here. Okay, so I'll copy and paste it here, and what do we have? We will have, okay, roughly, let's see. I will just bring these terms together. I'll just have alpha on the outside. Okay, dt dx actually scales with this alpha Ts minus T infinity over delta T squared. So it's this term over here. Okay, and if we were to substitute the term for V, we would actually see the same thing, more or less. Okay. So basically, we're just having a non-dimensional version of our energy balance equation. Alright. Okay. So this is the dt dy. Okay, partial t, partial y. That will scale how? It will scale as v over h. So okay, v over h. Okay. Oh, let me just copy and paste it here. Where's the v over h? Okay, Math Cal 01. So yeah, this is what I'm trying to say, and we'll just substitute this in. Let's just substitute this in. Alpha h over delta t squared. And we'll just see that it's basically on the same order of magnitude. Okay. Did I just? Oh yeah, that's the wrong O. the wrong bracket. Okay. Okay, so yeah, anyway, I will just stop for now. Yeah. But basically, you will just have del t del y also on the same order of magnitude as what we have before. Okay, sort of. Yeah, I will need to cancel the terms and all that. I'll just do that in the next video. But this h and this h will cancel out, and then we'll just have the same stuff. I'll stop for now. I won't let this video get too long. I'll see you next time. Bye bye.